Good morning. Thank y'all so much for coming and joining us. I would never dare speak for James, but I'm just going to go out on a limb and thank you to the OffensiveCon team for having us and throwing another great conference. This talk is the Print Spooler bug that wasn't. So James and I are both security researchers on Project Zero, and James is a master of Windows, and I like to look at in the wild stuff. And so that's how we ended up doing this joint presentation. It all started with this bug, CVE 2022-41073. And so in November of 2022, Microsoft released their advisory saying this was a print spooler elevation of privilege, and it was in fact known to be exploited in the wild. So as I'm going through in January trying to think about all of the different bugs from 2022, another elevation of privilege in Print Spooler caught my eye, and I couldn't find any other details about this bug. So it seemed like a great candidate to do a quick little root cause analysis in what was going on in Print Spooler. So I went through all of the different files associated with Print Spooler, looking at the October version and the November version to try and figure out what was this bug, what was the fix. And there was only one file that had been changed in that time period, and it was winspool.drive. And thankfully, within that file, there was only one function that had any change in it, and that was this load new copy function. So in October, during the vulnerable version, load new copy would immediately call activate activation context, and then immediately go into a load library call. In November, the change was simply to no longer do impersonation around that load library call, and after doing load library, then resume impersonation again. So this sounded interesting, because this sounded an awful lot like a bug from 2015 that my teammate here, James, had reported. So the bug in 2015 was James had discovered that when a privileged process is impersonating the calling process. They're trying to look at what does the user who's calling into this privileged server, what does their sort of operating system look like? It's going to use that user's device map. And that means that whenever these file accesses, such as a load library call is happening, it's going to use the user's device map, not that privileged process. And that can lead to elevation of privilege, because you can imagine that you have this privileged process that's impersonating a caller. The intention, if they're calling load library shared library.dll, is that it's going to go to the C drive, as expected, and then go to the normal Windows System 32, for example, shared library DLL. But in 2015, the case actually was if the user had done a symbolic link between to remap the C drive to a different folder, all they had to do is then create a Windows System 32 and then shared library DLL path in their custom folder that was now mapped to the C drive. And instead, that's what this privilege process would read. And so this fix looks an awful lot like what that bug was doing. So in 2015, they fixed this by adding an object attribute flag, which had the value 0x800, and in any load library calls, it would no longer use the impersonated device map and instead use the real one, for example. So if that was fixed, that couldn't be the bug, right? So what was going on here? Thankfully, went on VirusTotal to do some spelunking to see, can I possibly find this exploit sample online? And lo and behold, I did. And so what do? The first time you get an exploit sample is you run it on your machine. And what I ended up finding was while this was running, it created this new folder at the C drive. And what especially stood out was it's creating this sort of file system path that makes it look like it's the legitimate C drive with a Windows and System 32. But the only files they were dropping is first this print config DLL, which then when looking at load new copy is one of the DLLs that changed function would load, as well as these two manifests files that are under a WinSXS directory. I had never heard of manifest files. These whole path names seemed very convoluted and not clear to me what it was or what could be happening. So of course, what I do is, James, help me, what's going on here? What is a manifest file?
Thank you, Maddie. So yeah, I came in to help out, basically to try and use my, my Windows knowledge to figure out what this in the wild exploit was actually doing. So what is a manifest file? Well, manifest files are a component of a feature introduced in Windows XP called side-by-side assemblies. And the primary purpose of side-by-side assemblies is to resolve a common problem of early versions of Windows called DLL hell. This is Microsoft's term for this as well. It's not something which I'm just calling it for that for fun. The idea here is that Windows has various locations like System32 which are designed for shared libraries. Now, primarily those shared libraries are system shared libraries, so they're provided by the operating system. However, there's nothing stopping an installer for an application installing its own shared libraries in there if it feels that other people should share in its wonderful shared library footprint. So say, for example, you have application A. And application A thinks its shared library is the greatest thing ever, and so it goes, well, everyone is going to want to use it, so I'm going to install it in System32. Now, application A is specifically using version 2 of this shared library because it has the greatest, most amazing features in it. However, at some point, the user comes along and goes, well, I need application B as well. And application B, of course, in isolation, also goes, hey, this shared library is the shit, right? This is the greatest thing since sliced bread. So I'm going to install my own copy into the shared location. Unfortunately, application B is only using version 1. It clearly doesn't need those super advanced features in version 2. But it's just the same name, so it just installs over the original version application A installed for it. Now, the problem with this is, of course, application A is relying on these amazing new features which came with version 2. So when application A tries to load, it might not find an exported function anymore, or the actual functionality may just not work correctly. And so you get a crash, or the application doesn't start. And this is, of course, a real problem, because the issue occurs just because of the sort of ordering in which the shared DLLs are dropped. And technically speaking, application B might not run with version 2 either. So both scenarios are a problem. So the Windows side-by-side assembly functionality is trying to resolve this by actually allowing you to install 2 different version copies of that same shared library, but into a shared location managed by the operating system. So this is where we sort of, Maddie showing the file listing of what the exploit was dropping. This win SSX, win side-by-side folder on disk is where all these side-by-side assemblies are being stored. Now, there is, of course, a separate problem in that, of course, Windows wasn't designed for versioned DLLs. Like, if you look at the import table for an application, it just has a simple text string. It's not even a Unicode text string. It's like an ANSI text string. Now, you can like hack around this. Like, as you can see in this example, the VC runtime has a version number associated with it, but that's not really a scalable solution. Like, you've got to manage the versioning, and what if you want to have like a very small point release of a DLL for like bug fixes and things like that? Well, that's not going to resolve it either. So there needs to be, well, unless Microsoft were willing to change the entire import system, which seemingly was not what they wanted to do, they needed an alternative approach to handle this fact that imports don't have any versioning information. So what they came up with is like pure late 90s, early aughts technology. Let's use XML files for everything, right? XML, the greatest data exchange standard ever created. But of course, these days, you'd probably see this in JSON until something else comes and replaces that. And this application manifest is describing the dependencies associated with my application, so application A, for example. Now, it starts off with an element which identifies the application itself. So every user of these manifests should have its own sort of identity that allows it to sort of deconflict with, so for example, someone could depend on this application theoretically if it has its own identity. But inside of that is you have a list of dependencies, and these dependent assemblies are saying, I'm relying on shared library version 2. And so, in theory, when this is being used, when I try to use shared library.dll, I should get version 2 of that library, not version 1 of that library. So how is this actually used in practice? Well, Windows provides a set of APIs to create something called an activation context. An activation context is a binary structure which contains these sort of like information about dependencies associated with these manifest files. So for example, you can call the create activation context API, pass it the path to one of these XML manifest files, and it will do some parsing of the XML and construct this binary structure for you, and return you a handle. With that handle, you can now call activate activation context, and then certain system APIs, such as load library, for example, will now recognize that that activation context is in effect on the current thread, and perform the different operation and potentially do like dependency resolution for you automatically at runtime. Now, I showed that application manifest, and it had dependencies, but how does it actually find those dependencies on the disk? Because like, you might have actually like 10 different, subtly different versions of version 2 of that shared assembly. And if you look at the Win side-by-side directory, there's actually loads and loads of DLLs and directories in that location, which potentially are resolvable. So for probably good reason, what Microsoft decided to do is, inside CSRSS, which is a system process which runs in every single user session, which sort of controls access to the windowing system and things like that, they implemented a new service over RPC called the side-by-side server. And whenever an application A, say, calls create activation context, it makes a call to this side-by-side service, passing it the XML file, or path to the XML file, and say, hey, can you create me an activation context, please? Now, the side-by-side service will go through things like your dependencies, and it might have to try and resolve versioning information. So inside the Windows registry, there's a side-by-side key, which contains all the sort of installed registrations for these side-by-side assemblies. And it can say, for example, I want version 2, and it will try and pick the newest version of version 2 it can. So in this case, version 2.0.1234. And then it takes that version information and the name of the assembly it's trying to reference, and it uses that to construct a path underneath that Windows side-by-side assembly directory, which refers to what is called an assembly manifest for that assembly. And as we can see here, this is just an XML file as well. But you may have, if you have a keen eye, you may see like the path here looks awfully familiar to some of the paths that in the wild exploit was dropping. Now, once that's all resolved, the side-by-side assembly service creates this binary activation context. It can just copy it back to the original process, and then the original process can actually perform operations on it. It contains enough information that it doesn't need to keep going back to CSRSS for more information. Now, the assembly manifest file looks awfully familiar, like awfully similar to the application manifest file, but they are subtly different. The application manifest file is kind of saying, this is my configuration for my application. And it contains your dependencies, but also can contain things like, is my application auto-elevating? Like, should UAC show a prompt when I try and run this application? The assembly manifest file, on the other hand, defines what resources and information is stored in that assembly. Now, I've mentioned assembly, the word assembly, multiple times. It may not be clear what an assembly actually is. All an assembly is, in terms of Windows side-by-side, is a directory which contains resources of some kind. It may contain like lists of files, it may contain specific resource DLLs for different languages, for example. But that's all it's doing. All an assembly is like a collection of components. If you're like a macOS user, it's similar to sort of the application bundle. Like, the application bundle is a directory, but it's treated by the OS as kind of like its own thing, like a single entity. So in here, you can have subsequent dependencies, so you can have like, that dependency can have its own dependencies, but it also has, like, for example, a list of files. It might have a list of COM objects that this implements. But in this case, for our shared library, it just has a single file element which says, I contain shared library.dll. And how this is then used is, once this is parsed by CSRSS and returned back to the application, you activate the activation context and call, say, load library. The load library in the LDR load DLL inside NTDLL knows enough about the activation context to go, oh, right, okay, I've got this file, there's currently an activation context. Does that activation context tell me to redirect access to that file to somewhere else? So because we're looking for shared library.dll, it goes, oh, actually, it's in this assembly directory, which is basically that sort of like a string with the identity of the assembly, version number, etc. And so this is how those versions are resolved at runtime, and therefore getting rid of DLL hell, etc. Now, this side-by-side service has been exploited a number of times. So for example, just in 2022, there was also this vulnerability which was exploited by the Knotweed actor. I don't know what Microsoft are calling it now. They completely changed all the threat actor names. But this is like just a snippet of the blog post that Microsoft wrote, and it's talking about an issue with activation context caching. So perhaps this bug is just there's something called activation context caching. What is that? Well, activation context caching is just a performance optimization. You can imagine like searching for XML files and parsing XML files into binary structures can be kind of a complex and slow process, potentially. And if this has to be done every single time a process starts or tries to create an activation context, it could get quite expensive. So the side-by-side service inside CSRSS maintains a mapping between a certain key and pre-configured activation context that it's already parsed. And the problem with this, of course, in the Knotweed perspective, is that the key is not sufficiently secure that you can alias it. So a malicious application can come along and alias an existing manifest which is in a secured location on disk by aliasing that key and getting a malicious entry cached into the context cache. So ultimately, that application, once that application goes away, another application comes along and says, hey, I need to use this manifest file. It talks to the side-by-side service, and it goes, sure, like, based on that key, based for that manifest, I know I've already built the activation context for you. Unfortunately, that activation context is now malicious, and it potentially can load like evil DLL or something like that. So you've now compromised that potentially privileged process. Now again, this looks awfully familiar because I reported what as far as I know is the first public bug in this caching mechanism back in 2019. And in that case, the key, I believe, was literally just the path to the manifest file, or the path to the executable. So it was pretty weak, it was pretty easy to confuse. Now, over time, Microsoft have fixed various things, but it kept happening. Like, ZDI did a really good blog post about this, talking about the Knotweed exploit, also talking about some of the variants that were found. Every time Microsoft fixed something, someone would find a way of bypassing it with a new interesting technique. So I would highly recommend reading the ZDI blog post about this as well to get a better understanding of the caching. But a kind of upshot of a lot of this is, in theory at least, all these bugs should be fixed because Microsoft have put in the effort now. Like after 4 years, clearly these caching bugs are fixed. So we can probably assume it's not a caching bug. So what could it be? Well, it turns out that the example code I showed you was doing sort of manual creation of this activation context at runtime. And it could be something associated with that, potentially. But what is actually probably more likely to be happening is that when you load a DLL, that DLL might have its own manifest associated with it. And one thing you can do is you can embed that manifest file, that XML file, inside the DLL itself using a special resource ID. And if that resource ID, which is this isolation-aware manifest resource ID, which I think resolves to number 2, if that exists, it will actually, during the DLL loading process, create the activation context, and then use that to resolve imports for that library during initialization process. So it seems likely that that might be why this, what this in the wild exploit was using. So let me hand back to Maddie to talk more about that.
Relay baton change. So back to the exploit. We understand now this manifest file seems awfully interesting from here. So what is actually this exploit doing? First up, so the interesting fact of, after learning all this, print config DLL does in fact is an isolation-aware manifest embedded within it, which means, going back to what James just said, that if it is loaded, it is going to go ahead and load everything that is included with it and process that manifest. So how does this exploit work? The first thing that it does, as I showed before, is drop that file tree at the root of the C drive, calling myFakeRoot. It then does a symbolic link to change the mapping of the root C drive to its myFake folder that it planted there. So now the C drive has been modified, by this normal user running at medium integrity. It will then use RPC to start the print filter pipeline service using the begin print function, which then ultimately calls into that load library function that had been patched within winspool.drive. So we're going to now load that print config DLL. Because of the patch from 2015, the actual print config.dll, which is loaded, is the legitimate one. It is not the one at the modified C root drive. So that is not the bug. Like the one in 2015 of load library being able to load from the impersonated device map, that is not what we're looking at. But what does happen because of that isolation-aware manifest is that as print config is being loaded, it's going to call into the side-by-side service to begin processing the embedded manifest. But side-by-side service has not had that same fix as load library did in 2015. So side-by-side service, when it's looking for this manifest, is going to in fact use the impersonated C drive, and thus whatever manifest is at the user wrote into that myFakeRoot folder. And so what the exploit did is it took the legitimate side-by-side manifest that print config depended on and added this extra block in there, a dependent assembly. And as we heard from Dave this morning, the bug is a bunch of dots and slashes, as we can see here. So they added a dependency using directory traversal to get up to their impersonated C drive and to say, hey, you're dependent on this myFakeRoot. Oh, I highlighted it. All the dots and slashes. And so now that side-by-side service knows, hey, we're also dependent on this other assembly, it's going to go back into the impersonated C drive to grab that myFakeRoot manifest. And the myFakeRoot manifest specifically says, hey, you're going to be dependent and need this file print.vbt.dll. Because this is in a dependent assembly, it's going to first look within that same folder of myFakeRoot. And so now we've loaded, or we've crafted the activation context within this privileged process. Print filter pipeline service is a local service which runs under system integrity, and it's going to look and load myFakeRoot print.vpt.dll. And so the exploit had taken the legitimate print.vpt.dll and just modified it so that immediately upon load, it would begin running this function, which they had changed, so that first, they turn off impersonation, and then second, they're going to load their malicious DLL. And so now, within a process with system integrity, they are running their malicious DLL and have an elevation of privilege. So how did Microsoft fix this? We talked about the very first patch they did. And if you're looking at this and being like, but wait, isn't that just breaking the exploit? Yes, you would be correct. So they did follow it up the next month in December with changes to the side-by-side service to create a broader mitigation. So here within side-by-side service, where the function base p xs create file stream x, they have this new code, this block that says if this new feature assembly manifest redirect trust is enabled, that's just a feature flag this new mitigation is behind, and these flags equal 7,000, we're now going to pass to NT open file. Oh, I did great highlighting again. We will pass the same object attribute that they had added to load library back in 2015, now we will use that in side-by-side service. So this is the object ignore impersonated device map. But to do this, going back, first we need to figure out what were those flags. So those flags to enable that mitigation there are only set if, first, the process is running at the system integrity level. So this is important to remember because there's lots of other processes within Windows which could be interesting targets which aren't in fact running at the system integrity level. And the second one was when this is called base p create activation context within kernel 32, it has to be impersonating at that time. The final is looking at, is this mitigation enabled? So we're looking for some sort of global variable kernel base assembly manifest ignore impersonated to see if that is set, then we will set these flags that are passed to that previous function in side-by-side service to that value 7,000. And when we then go back further to figure out where is this global variable set, it's within kernel base. So set process mitigation policy. And so they've added this whole new block in December 2022 to the set process mitigation policy, which allows processes, as it sounds like, to explicitly set different mitigations for themselves. And so they've added a new one. This enumerated value is 17, and they've given it this name in the SDK, process user pointer auth policy, which clearly does not describe what this is doing, but yeah, so it's number 17. And so if the feature flag has been enabled, then they will set that value. And so what that comes down to is that the process has to explicitly say, enable this mitigation for me. It will not be enabled for processes otherwise. And the thing was, is I saw all this code, and I wanted to run the exploit and look at it and see, hey, has the root cause now been fixed? And it wasn't. And I tested that by looking at just that print filter pipeline services code and just skipping over the reverting impersonation, because we know that was just blocking the exploit, not actually getting to that root cause problem. And yet in December 2022, I see all this code here in side-by-side service, but it's never being run. And that's because it wasn't until January 2023, which they finally added the mitigation to print filter pipeline service, where they actually enable the mitigation for side-by-side service. So has this addressed the root cause? What is the root cause? In my point of view, the root cause is actually going back to the same root cause of the bug back in 2015, 8 years ago, if you're also unsure of time at this point after the last few years, that the user is able to remap that root C drive for privileged processes. That's the root cause here. Why should a unprivileged user be able to do that for privileged processes? And so each different fix up until then has been these point fixes to try and confront that issue.
So yeah, the Indowad exploit is obviously quite interesting, but it's something which we want to look at. Is like, here's this. We've already seen there's been a number of side-by-side assembly vulnerabilities in the past, but is there more to it? Has Microsoft done due diligence here and actually finally fixed the bug, other than the fact that they've not fixed the root cause? So I thought we should go back into some variant analysis and see if there's any sort of similar bugs in the past that we might have missed. And so Maddie was obviously looking around again, and there was another bug from May 2022. And the name of the report was Print Spooler Elevation of Privilege Vulnerability, which is awfully similar to the one fixed in November. This one was attributed to a researcher working with ZDI. Interestingly, also the NSA, quite where the NSA came into this, who knows. But that is worth a look, right? Like, it's similarly named. Maybe it's the same bug, maybe it's a different bug related to it, or maybe it's completely unrelated. Print Spooler has had quite a few bugs over the years, so it wouldn't be a complete shock that it's something completely unrelated. Now, after a bit of splunking again in VirusTotal, it was actually possible to find a proof of concept for this. Something like, you might not necessarily realize that, obviously certain detections from certain AV companies will put the CVE number in the detection string. So you can actually look in VirusTotal, if you're particularly looking for an interesting a vulnerability with no public proof of concept, well, try and look in VirusTotal and see if you can find a detection string which has that CVE number in. And it might just happen to be a proof of concept for that vulnerability you're looking for. So what is the bug? Well, it's exactly the same bug, except it's a different process. It is pretty much literally the same bug. Like, everything about it is the same. Instead, it's exploiting the main print spooler process instead of this print filter pipeline service. But yeah, other than that, like the whole manifest trick and all that sort of stuff, basically exactly the same bug. And unsurprisingly, Microsoft fixed it in exactly the same way. They did a point fix to fix the proof of concept. Now, it just was a different DLL. In this case, this is the local spooler instead of the WinSpool drive. But like, you look at that and you think, how did Microsoft not like try and fix the variants of this? Because there must be plenty of places they could relatively easily find that, because this was still loading printconfig.dll. It was even loading the same DLL. So you'd think, why could they not notice that this bug existed in other places? But it took until, of course, we don't know, of course, the timelines of when the in the wild was necessarily found relative to when the May 22 bug was initially submitted to Microsoft. So we don't know the sort of timescales of this. We don't know, for example, if in the wild bug is just a reverse engineering of the May 2022 patches and just re-implemented. It is completely different code, so it's not like they've necessarily taken the original exploit and just changed the sort of entry point to the loading the vulnerable DLL. So who knows? But interestingly, in the spool serve itself, they turned on this mitigation policy. Now, if you remember from only minutes ago, Maddie said that this mitigation policy was only added in December 2022. So clearly, Microsoft were thinking ahead here. They were developing what they would consider to be a broader mitigation for this. And they even could turn it on at selectively used based on a feature flag. But the code to actually implement this feature just didn't currently exist. And that's kind of interesting to see, at least certainly in shipping code, as opposed to, say, an insider build of Windows. So though, of course, this got me thinking that clearly the root cause isn't fixed. And in fact, this mitigation is so weak and like it requires it to be enabled. Like, how many processes even have this mitigation enabled? Turns out when I did like a basic analysis, there is only 2 processes with this mitigation enabled: SpoolServe and Print Filter Pipeline Service. So any other system service which runs at system integrity could be vulnerable. Well, even if you're running at high integrity, you can't even turn the mitigation on, so you're kind of stuffed before you even started. But even like system services which could benefit from this and could potentially be loading DLLs during impersonation do not have this enabled, so it's not a broad mitigation. So of course, you may be thinking, hey, I would like to find some of those bugs, right? Like free bug bounties from Microsoft or what have you. So here's some at least tips of how you would go about finding similar bugs. The first one is just use Process Monitor, right? You can build up a filter in Process Monitor to look for what look to be DLL loads. In this case, we're just using createFile because createFile is the only event which captures the impersonation state. Unfortunately, when you actually get like the load DLL event, it doesn't catch the impersonation state in that case. But it doesn't really matter. You can filter out enough, just look for executable access being requested for a DLL file. Inside, say, a system process or a local service process or a network service process, and just basically just stick it running and use your system and see if anything interesting pops up, right? And this will print out the process that it's trying to do the load. It will also obviously show you the path to the DLL that it's actually trying to load in that case. You can, of course, also use Process Monitor stack tracing, so you can open it up, the event, and just look at the stack trace and see how you might even get to that in the first place and how you get that DLL to load. So that's the first thing. Can you find any instances of where this is loading? Of course, in this particular example, SpoolServe is already fixed, so tough luck. You can't take this and find an exploit there. Well, you might be able to, who knows. The next thing, of course, is you want to check, does that process have this mitigation enabled? Because of course it's in theory useless if this mitigation is enabled, because you probably can't exploit at least the very specific vulnerability that it's exploiting. And for this, you could do more complex analysis, but if the process is running, I just basically looked up the address of the global variable out of kernel base and just read it out from memory. Very simple. If it returns you a 1 for that single byte, it's turned on. If it returns 0, it's turned off. And of course, in this case, SpoolServe has it turned on, so no luck there. And then finally, you probably want to look at the DLLs that it's loading. So if you could find a bug where you could control the exact path of the DLL to load, then you don't need to worry about all this manifest stuff, right? You just tell it to load your arbitrary DLL for you. But of course, what's more likely to happen is a DLL is being loaded from system32 or some other location which you do not actually control. So in order for this exploit or for this vulnerability to work, it needs to have that specific embedded manifest resource. So again, for example, this Windows storage.dll was in that printout from process monitor. If you look at the manifest, unfortunately, it's not an isolation-aware manifest, so this would not be loaded automatically during DLL loading. So there might be some way of exploiting this particular DLL load, like if it does something specific in DLL main, for example. But in general, you're not going to be able to do very much with that, at least in terms of this vulnerability. However, this manifest does have dependencies. So the key to the way in which the exploit works is you need the DLL, the original manifest is of course embedded in the DLL, so you can't modify that directly. So you need a dependency which comes in from the file system that you can redirect using your fake C drive, and then basically use that to take control of the DLL loading process. Now, if you actually then try and do an exploit for this, there's a reasonable chance that something doesn't work, and it will not entirely be obvious why it doesn't work. So fortunately, Windows comes with a tracing tool, SSX trace, which you can run to start generating a log of all side-by-side assembly events which are occurring. And you can basically start that up tracing, run your exploit, your proof of concept, and then stop it, and then parse the trace, and then see if you can see if it's failing in a certain way. Like, it will give you sometimes reasonably good errors. Like, if you've made a mistake in your XML file, it will tell you the line number in your XML file that you've made a mistake in. It'll question your life choices and all that sort of stuff. So it's all very good. And you can see from like a little snippet here, this is actually the vulnerability in operation, in the wild one. And you can see how this .. thing is working. It's literally going, I wonder if there's a manifest file in this directory plus this assembly name, which I'm just going to concatenate straight onto the end of the path. And so it ends up with like a file traversal and stuff like that. Now, it's worth pointing out the file traversal stuff is something which has been reported to Microsoft, as far as I know. Like, it's in the ZDI blog, for example, but it hasn't been fixed. Now, I'm sure there's a compatibility reason there, but it does feel slightly wrong that they're going to literally doing like 90s era like vulnerabilities in terms of just concatenating a potentially untrusted value just to the end of the file path. I suppose they argue, well, it's not like you can override the location of that manifest file, right? Can you, right? Anyway, that's beside the point. So of course you might be asking, like, did I actually bother to do any of this, right? Like, it sounds like a lot of work. I did the work really for the screenshots, to be honest. But maybe we can demo something, right? So this is my Windows 11 machine. It is running the May Patch Tuesday patches, so it is completely up to date. If you ran the in the wild exploit, it wouldn't work on this machine. And of course, cross your fingers to the demo gods that if I run that, come on. Okay, so we get a command prompt. If I do who am I, we're now running as And so it's worth pointing out that that is literally, it's pretty much the exact same back-end exploit to the vulnerability. All it is doing is literally changing the entry point to the whole load library process, right? If you can find that entry point, potentially you can find your own bugs. Now, this has been reported to Microsoft, but we'll see how long that takes to fix and what they will actually do to fix it. it'd be kind of interesting. So let's just wrap up some final thoughts. So I think, obviously, this whole side-by-side assembly stuff has been exploited multiple times, at least twice in 2022. And it's quite a complex piece of code. And it seems to be, why is it running in like a privileged process and all that sort of stuff? It's potentially even like accessible from certain sandboxes like Chrome. But that's beside the point. And so it doesn't feel like the kind of thing that should be, Microsoft needs to do a better job of trying to fix this. And fundamentally, the problem is, like, the root cause, the sort of 20-plus-year-old design decision to allow the user's impersonation drive maps to be passed across the link, passed across, say, RPC, and then allowing that user to replace the system drive seems like probably a bad thing. Now, of course, there's also further issues that, like, why, for example, if CSRSS is really only concerned about the process which it's talking to, like that specific process, why is it using impersonation at all? What purpose does that serve? Like, all it seems to be serving is providing a potential attack vector for exploitation. So it would be really nice, of course, if this got fixed more systemically, that actually, like, the proper root causes were fixed, rather than relying on typical sort of breaking the proof of concept and things like that. Unfortunately, that might be a bit too much to ask for sometimes, but we will see what happens. But yeah, it's been a very interesting insight into sort of, for me certainly, not doing too much of the in the wild stuff. That you can sort of see where they've just taken a very simple path and produced quite an interesting logical vulnerability. So yeah, thank you very much for listening to us. I guess we could answer questions, but me and Maddie will be kicking around for the rest of the conference. So if you just want to grab us somewhere else, then go ahead. But if anyone's got any questions now, then fire away.
Going once, going twice. Okay, we're done. Thank y'all.
Thank you.